In this video I want to start investigating the problem with the display on this HP9845B vintage computer. I've been going through this machine and trying to restore and repair it, and found various faults. There are still quite a number of faults I'm aware of, but I want to go through this in a logical sequence if I can, and ultimately we'll run some test code on this, but just to try and keep things interesting, I want to go through using its own code if at all possible, and so that's what I've been doing. And in trying to resurrect a machine like this, it sounds a bit counterintuitive, but because it's such a complex machine, it can give you a lot of clues as to where particular faults may lie, and the more complex the machines are, then the more clues they can give you. And it's just really trying to work your way through, and where it really gets complicated is where there's more than one fault at a time. So it's a bit like trying to do a crossword where one or more of the clues is wrong, and where the words intersect it kind of gets a bit confusing and it can be difficult to decipher what's going on. And the same is true of a machine like this. When you get various faults that can interact, it can be difficult trying to figure out what the machine is actually doing. But if you can try to subdivide it into its discrete sub-assemblies and subsystems, then what you can do is focus on those individually, and that's the approach that I tend to take, and that's what I'm trying to get across in these videos. So we started with the power supply, actually we started with the chassis, then the power supply, then the keyboard, and we've kind of progressed through now into the system, and it's starting to get to the point where it's coming back to life, but there's quite a way to go yet. The two processors do seem to be trying to start up, but we're getting nonsense on the screen, and that's what I want to address in this video. I want to start looking at the display output, see if we can get any closer to getting a sensible display. We'll have a look at what it's doing in a minute. But you'll notice that things have changed a bit here. Normally what I do when I'm working on something like this is use things like this to connect the monitor, and this allows me to rest the monitor on its side, usually facing backwards because of the way these connectors are arranged, and that wouldn't really work very well here because I'm trying to make a video. So for the purposes of the video, I've gone to the trouble of making up this aluminium frame, so the entire monitor is now on a frame. You can see it's very rigid and it's quite a strong structure. I'll show you this next time I take the monitor off. But it's allowed me to put the two riser cards, the two legs to the monitor, onto some risers, and then the risers and the boards are now screwed to this aluminium frame, and then I can put the monitor on top of that. And what that allows me to do is gain access to the two riser cards, but also I can put the other cards in risers as well if I want to, without having to remove the monitor. And so it will make these videos flow much more smoothly. I'll be able to explain what I'm doing. And also there are a number of faults with the printer. So I know there's some faults on this board, and I know there are some faults on this board. And to work on either of these, I need to either remove the monitor or find some workaround for connecting it. And so making this frame for these videos seemed to be the best course of action. I'm not saying you necessarily need to do this if you're working on one of these, but for these videos it should make things a lot more interesting and easy to follow. So the next thing I'm going to do is point the camera at the screen. We'll see what we're getting, and we'll go from there and try and figure out how to get this up and running. I'll power the HP up, we'll wait for the screen to warm up, and you'll see what the next fault is we need to try and address. So as you can see, the screen is starting to come back to life. We are getting text on this, and if I start pressing keys, you'll notice that they appear on the screen, but they appear in multiple places. If I press clear, it takes us back to what we started with. Now that's a good indication that quite a lot of the system is working. And in particular, because of the way the operating system which is what we're now running on this, works, it relies on being able to create dynamic tasks in software, and so that means that a great deal of the system has to work for this to actually get this far. But notice we're getting some weird characters appearing on the screen. We're getting these repeating blocks, so something's not right, but we are getting some of the correct text. So for example, it's saying memory test in, and then the rest of the text is missing at the top. So it is starting to try to put out proper text. It's a good indication that the operating system is fundamentally running. So why are we not getting the right display on the screen? And there are some clues here, and like I said, if we look at this as if though it's a puzzle, we can actually deduce quite a lot without actually starting to delve into the electronics. So firstly, although it appears that the keys are correct, so if I press the Y key, we're getting a Y on the screen, we're not getting the correct characters all the time. If I press the 1 key, we should of course get a 1, but we're not. We're getting a Q character. And if we press the 2, we get an R. And so if you're familiar with systems like this, you'll realize that that indicates that one of the bits seems to be stuck, in this case bit 6. So instead of getting a 20 for a space, for example, we're getting a character that represents a value of 60. And what's effectively happening here is bit 6 of the character value is stuck, so where we should be getting a space, we're not. We're getting this little hyphen character. So that's true of all the characters. Whichever key I press, the character we get is essentially the wrong character, and it's the character you would get if you were to always set bit 6 high. So it sounds like there's an issue with the buffering. Unfortunately, it's not quite as simple as that with this machine. The other issue we've got is this repeating text. Now it could be the same fault. I suspect we've got at least 2 faults here, and when I first saw this I assumed this was a memory decoding issue. You probably recognise this is the sort of pattern you get in systems where there's a stuck bit in the memory decoding and it just keeps reading the same bit of RAM over and over again. I don't believe that's what's happening here, and I'll explain why as we go through this video. So the first thing I did when I saw this was to count the number of characters in each of these blocks. So taking any one of the characters that can be identified, we know there are 80 characters per row. If you count down, it's actually 3 rows, and then count across till we get to the same character again. And it comes to a total of 276, which kind of surprised me a bit. I was expecting something that was a multiple of 2, simply because this is normally caused by 1 or more stuck bits, and so you'll get a fairly well defined number sequence when you encounter that. The number of characters in these blocks doesn't make a lot of sense if it's a stuck bit in one of the address counters. So what I'm going to do is I'll turn this off and just briefly explain how the circuit works, and then we'll start trying to figure out what's going on. So there are 2 main circuits involved in what we're going to look at here, at least initially. One thing I should point out here is this could still be a problem with either the PPU hybrid module, could be faulty, or there could be an error in one of the ROMs, the system ROMs, or there could be a faulty RAM chip in the system. Again, I don't believe that's the case, and the reason I don't believe that's the case is because the process has started up for handling the keyboard, the process has started up for handling the display, and they're very reliant on the ability of the system to read the ROMs in both the PPU and the LPU, and also to save and retrieve values from the PPU RAM. It's still possible that certain cells within the RAM are faulty, but I don't believe that's the case. It might be proved wrong, but we'll investigate this as we go. I'm just taking you through this from the start. I haven't investigated this yet, so what I'm really doing here is taking you through my line of thought, just to try and make the repair as interesting as possible. And I've been asked to show more of this, so hopefully you won't find it too boring. But I tend to go through things in this manner, and it generally works. It does tend to result in repairs most of the time, not always. So the two circuits we've got here, this is the circuit that's on the logic card that's fitted to the CRT monitor itself, and this is responsible for generating all the timing signals within the monitor subassembly. And so this is really a series of counters. If you've seen my video series on designing a Z80 computer, then this is really the video output section equivalent. We've got the character ROMs up here. We tested one of these. The second ROM is still removed. I haven't refitted that yet. We don't need it to do the initial testing. But what we can do here, and this is where an understanding of the way this machine operates will come in very useful, because it doesn't necessarily operate the way you might think it would do. Most systems that employ scanning CRT displays will go through every single memory location every scan and essentially transfer the information that's in the RAM onto the screen. This doesn't necessarily do that, and understanding the way this operates will make more sense hopefully as we go through this video, and also explain why I don't believe it's just a simple counter fault in this case. When this is scanning, there is a state machine on the second of the two circuits we're looking at, and this is the circuit that's on the riser board that's in the leg that connects the monitor to the main unit. And there's a state machine in here that's comprised of a couple of proms, a couple of counters and some latches, and this goes through a sequence, and it's a bit like kind of pseudo code that runs in these proms. It's very simple. It's only 32 bytes in each one, and so that's best a 16-bit value, 32 16-bit values. Not all of them are used, but it provides a sequence of controlled events that control the way that the display system works. So it decides when latches are going to be latched and that sort of thing. But this is, as I say, running a kind of code in effect that can be manipulated from these circuits. So there are feedback lines, not many, but some outputs from this circuit that can control this, and also there are some control characters that the main unit can use to control this. It can reset it, reload the counters, for example, based on the value coming out of this. And that's where I believe the fault lies in this. So what we actually have in this is we have the interface between the video system and the PPU hybrid module. So on the PPU hybrid module there is an address data input output bus, 16 bits, and it's used for feeding data into and out of the PPU. This is connected inside of the main X and Y bus buffers, so it connects directly to the PPU hybrid module. This is a bidirectional buffer, and it allows us to get data into our video system. Usually it comes from the system RAM, and it also allows us to feed out a value to the PPU, and that is the address of the next data that we require. So 16 bits coming in. The buffer for the video is at address 7000 hex or 70,000 octal. And so to get us to that base address, we have the 16-bit address value. You probably can't see this, but if you look on the schematic for this, the upper 4 bits are hard-coded to give us a value of 0111, and that takes us to a start value of 70,000. The other remaining 12 bits are to allow us to increment through that buffer. So it takes us from 70,000 octal upwards, of course, as we count. And that's where I initially thought the fault was going to lie in this. I thought it was one of these counters had failed. So the way this system works is these count to the next address that's required. That value is fed out to the PPU. The PPU obtains the next data value from that address and then feeds it back into this system. Comes in as a 16-bit value, and that comprises of either 2 characters or a character and some status bits that are used to control how the character is displayed. When the data is fed out, the value is incremented, it's controlled from the state machine, and then the next byte is, or word is obtained. They come in, they are latched using these 4 latches. It's latched as 2 8-bit values. That is then it's basically selected as one of 2 pairs, so it's either this 8 bits or this 8 bits, and these are tri-state buffers. That 8-bit value is then fed along to this part of the circuit, and this comprises of 2 80-byte or 80-character shift registers. So this effectively contains a buffer for a line of characters and then another buffer for another line of characters. So the data comes into this. These are circulated through, so this runs through at high speed. It's constantly feeding data through here. Comes out, and you notice there are 12 bits. So we have 8 bits for the current character we want to display, and then another 4 bits are for the particular characteristics that we want to apply to that character. So we get these 12 bits. The lower 7 bits are for our standard ASCII code. The 8th bit is the chip select bit that we repaired in the previous video, and that gives us the ability to select one of 2 character ROMs, so effectively gives us an 8-bit value for 256 characters rather than 128. And the upper 4 bits are used for either cursor control, inverting the character, make it inverse video, making it blink, or underlining it. And these are fed through these multiplexers so that the system can select either this buffer, this line buffer, or this line buffer. This arrangement up here is used to control when the control data is coming in, so that's when these 4 bits are being fed through. That comes through this, and it's just using 4 of the bits that are coming through on the data. So a very simple system. But what complicates it is the fact that some of these bits coming out of these latches can be used as control characters, and so they can be used to reset the count or cause the state machine to jump to a different part in its pseudo code. So to try and explain exactly what's going on here, we'll start at this end. I'll attach a scope to the 3 control lines for this. So that's the NW, new word, new line, and new page outputs. There are test points on this card. So I'll attach the scope to that, and we'll just check this is running. I suspect it is, because if it wasn't, we'd get either nothing on the display at all, or a distorted display or garbage on the display. But the fact we're getting a properly formatted and structured display means that this is almost certainly working. But I'll get this hooked up anyway, and we'll have a look on the scope and just check these signals are what we expect them to be. So I've got the scope hooked up to those 3 test points, and what we're looking for here are the properly timed signals indicating that the system counters, the video system counters, are running as they should do. As I said, I'm pretty sure they are, otherwise we wouldn't be seeing the display as we are, but we'll just test this anyway. So I'll get this powered up, and sure enough we are seeing exactly what we should. So we'll start off, let's get the cursors, and we'll check the interval between the pulses on the blue trace. Okay, so that's about right. It's supposed to be 641, it's showing 640, but within the accuracy that I can see from here, that's good enough. We'll now zoom in and look at the next part of this trace. Just bring this one down a bit. And that should be about 225 nanoseconds, and it is, and the same with the next part should be the same as well. So that's working fine. This essentially means that the scanning systems are doing exactly what they're supposed to, and we're getting the correct timing, we're getting the correct intervals, so it's not like the timing's out because the scan frequencies are wrong. The counters must all be working, and that includes the counter on here. There's a counter on here to count the number of characters in each row. That controls the filling and circulation of the line buffers. That must also be working, so something else has to be going on here. So what we'll do now is we'll look at the address counters. I'm pretty sure these are working, but we'll test them anyway, make sure that all the outputs are working. So we should get 12 bits. Not all 12 bits are likely to be toggling. It kind of depends on what the system's trying to display, which is what I'm kind of leading up to. I've got a feeling that this is more to do with what the system is doing in terms of interpreting the incoming data, rather than there being a hard fault in the addressing. But we'll work our way through and try and confirm that. So next thing, we'll check these counters. So this is where it comes in handy, having the monitor raised up. It gives us direct access to this board, so we can probe it directly. This gets very difficult if we don't have the monitor fitted, because this will effectively not be doing anything without the monitor, because it won't be getting the signal coming back from the monitor to ask for the next data. One other thing I like to do when I'm working on systems like this is try and speculate as to where I think particular faults are. Now, I think there are at least 2 faults on this, but my money is on this particular IC, and the reason I think it's this one is because this is because we know, roughly speaking, where the bit error is in the data that we're seeing. We know which of the devices is responsible for handling that bit, and so this device is responsible for latching the data that is being used as part of the control. And just to kind of clarify that, we get 2 bytes in effect of data for the characters, but only one of these pairs is responsible for passing control characters, and I think it's a control character that we are looking for here, and that goes through these 2 devices. And because of the particular control character that is causing it to do what I think it's doing, that has to come through this device, and this is U38, so I'm pretty sure it's either this or we've got some strange issue with the buffer. It's very unlikely to be over here, because the data that's being shown is actually correct, it's just repeating. But I think what's happening is, I've got a feeling that the data coming through is not updating in the way it should, and when it sees certain values, it's causing this to reset the state machine. Because that's the only way you can explain the count that we're seeing in the number of characters in each of the blocks we're seeing on the screen. Okay, so what we'll do now is we'll check these counters, and all I'm going to do is probe the outputs, and what we're looking for is a good signal on the output of each one. There's nothing else connected to these, they go directly to the outgoing buffer, and so there shouldn't be anything interfering. So if we're not seeing a signal, we know something is wrong, so we'll check these, make sure it's working. So we'll start with the first one. That's working, and the next. So that's all 4 bits on the first one are fine. We'll go to the next IC, and you'll notice the frequency is dropping each stage, as it should. Okay, that's good. And then the last one. Okay, so all the counters appear to be working, so that's what I expected anyway. So all these seem to be doing what they should do. But what I want to do now is look at the load. These are loadable counters, and I think what's happening is these are being loaded when they shouldn't be, and that's what's causing the this kind of block effect on the screen. I think it's just rereading the same part. We can test that by looking at the load pin and seeing if the interval of the signal on there matches what we're seeing on the screen. We know that it's a 60 Hz refresh on the screen, so we should be able to work out what we're seeing and if it makes up or makes sense with relation to these signals we're seeing on here. So I'm going to look at the load pin. They're all connected together, but I'll look at the load pin on one of these and we'll see what we get on the scope. Okay, we'll do a single capture there, and then we'll do a check to see what interval these are at. Okay, 4 milliseconds. So if you recall, it's a 60 Hz system, so around 16 milliseconds per frame. And so we're getting a reload of the counters at exactly 1/4 of the interval rate. So it is starting to look very much like this is a problem with the counter, the address counter, being reloaded when it shouldn't be. And that can be done in response to the system receiving a control code through one of these devices, so it's either this one or this one, that aren't passing on the correct data value. That can also explain why we're seeing odd characters on the screen. It's just not passing on the correct character for certain rows. You may also recall in the previous video that when we first started looking at this, we had alternating lines. One line was showing a block of solid characters, the next was showing random text, the next was solid blocks. It was alternating between the two. And that's the kind of effect you would get if one of these pairs wasn't doing what it was supposed to. So all these clues kind of add together and point you in the right direction. But what I want to do now is attach the logic analyzer. I wouldn't normally do this, I'd normally move straight on and try replacing this device. But I'll attach the logic analyzer just to try and confirm, for the sake of the video, what I've been trying to describe. I'm not making it very clear here what is going on. But the logic analyzer will be connected to the PPU test connector, so it's effectively connected to these points for the address and data bus. But what we'll do instead of using the main system clock is we'll connect the clock on one of the pods to the control pin, the enable pin for the address out latch or buffer. And that means that we'll be able to capture the data, the address values that are being sent out, and this should be incrementing from 0 up to the capacity of the monitor. So it should be going from 0 up to about 1,000 and then back to 0. But I suspect it's not doing that. But I'll attach the logic analyzer, we'll see what's going on and go from there. I've loaded the standard configuration I have for the HP9845B. We do need to make a small change to the configuration because, as I said, I've connected the clock input of one of the modules to the enable pins of the address buffer on the CRT interface card. So we'll go to setup and we'll just change the configuration. So what we want to do is disable this clock. It's the main system clock we have been using on pod 1, so we'll disable that. And I've actually got the clock line on pod 3 connected to the enable pin of the address buffer on the interface card. And although it's enable low, we actually want to use the rising edge, because if we use the falling edge, the address will not have propagated through to the output pins at that point. So we want to use the rising edge, and this will enable us to capture the data as it's sent out, and it will be the address that is being sent out to the main system. So it's now configured. We'll enable the analyzer and we'll power up the HP and see if we can actually capture anything. And we have indeed captured something. I'm going to just refresh this, make sure it's running continuously, which it is. And as you can see, we've come through to 7C82. I'm just going to compress the scale a bit. Got the same on the screen of the HP machine, by the way, so that hasn't changed. So 5 microseconds of division we're now showing on the analyzer, and you can see the address is 7C82, and if you recall, the buffer for the CRT display starts at 7000 hex. These are hex values, by the way, and they're in the PPU RAM card, which is block 1. So you can see the block address is indeed 1, and the address is falling within the range we're expecting, and it is incrementing, so we are successfully capturing the data coming through the buffer. So we'll keep scrolling across now. You'll get these long delays depending on what the system's doing. We'll scroll across, we can see it's incrementing. We'll keep going across now and see where it resets. And it's now reset, it's gone back down. So we'll just go back to where the reset occurred. So it's resetting here. You can see it's gone from 7DAB to 7CA1. So this is an odd value to reset to. It can do this, it just depends what value the system wants to load into the address counters. But I suspect this is wrong. But what I'm going to do is calculate the difference between these two values. So get the trusty calculator, and I'm going to enter, you probably can't see this, too dark in, let's get a light. Hopefully you can see that. So hex values, but we'll enter 7DAB, and we'll subtract from that 7CA1. And the value we get is 10A hex. And if I convert that to decimal, and the result is 266. So you may recall that's the number of characters we were seeing in each block of data on the screen, and then it was repeating. And this now explains why. It's going through a particular part of the buffer, resetting, going through the same part of the buffer again, and it's doing that over and over again, but it shouldn't be. This should not be reloading at this point, and the fact it's reloading means there is something wrong going on within the control board. And as I say, it's most likely because it's receiving a reset command or reload command. We saw the reload signals going low on the counter, and the only place they can really come from is the state machine. So either there's a weird fault in the state machine, or there's a fault in one of the incoming data buffers and the wrong values are being fed through to the system, which is more likely, again, because we're seeing rogue characters on the screen. So that would also explain why it's doing that. So I'll relocate the camera and we'll see if we can repair this particular fault. So I'll disconnect the logic analyzer from the boards. Get that out of the way. And so, as I said, the most likely cause of this is a rogue control character coming through, because these are not doing what they're supposed to. Hope you can see this in a bit of an awkward angle here. So what I'm going to do is the same trick I tried in a previous video of piggybacking another IC on here. Now you've got to be careful doing this. I'm only doing it here because the only things that are connected to these are devices I have replacements for. I would not suggest trying this technique on something like this, where it's connected directly to the hybrid module. You could damage the hybrid module. And also, because these are in pairs and they've got tri-state outputs, but they are predominantly working, and the correct characters seem to be, or at least to a certain extent, seem to be appearing on the screen, we can be fairly confident there are no dead shorts on the outputs of these, otherwise it wouldn't work to that extent. So I think one of the outputs is open circuit on this. We could try the techniques. We could attach the logic analyzer check the input and output based on when they're being latched and see if they match. But the easiest solution is, as I say, just to piggyback another device. So we'll start off with this one. It might not be this one, it could be one of the others, or it may be something else, but I suspect this is the device that is the culprit. So as you can see, I've piggybacked a new device on top of the one that we think is faulty, and we'll try and power it up. I'll move the camera first so you can see what I'm seeing. Okay, we'll power it up. Well, it's not perfect yet, there's still issues, but as you can see it is a step forward. We do seem to be getting what amounts to a proper startup screen. We're not getting the repeated text anymore. We're getting the correct text showing on the screen, but with still some rogue characters. The operating system does treat different areas of the screen in different ways, different code handles it, and so we do still have some issues here. One thing we can try doing, one of the tests it states in the service manual is to enter the word beep and see if it actually beeps. It's one of the reasons for trying to get the keyboard beep, the sounder working, because the beep is quite a useful tool to use. Unfortunately, the machine will also beep if it's a fault, so it's not always that useful, but now we're getting something on the screen. It is a bit more of a useful test. So we can enter beep, and you can see we are indeed getting the correct text on the screen. I hope you can see that. I'll press execute, we should get a beep, and the screen has cleared. If I just try entering something that's not a correct command, so in this case just beep EE, and we hit execute again, we should get an error, which we do. So that's a good sign. It means the system can not only respond to the correct command, but it can also identify incorrect commands. So that's a very good sign. I'm going to try pressing the clear key, and that clears the screen, and try entering some more text. Still getting the wrong text coming through, so that should be a 1. I'm pressing the 1 key. We're getting the wrong characters, so this is the second fault I mentioned. I did think there was more than one fault. So that's what we'll look at in the next video, see if we can track down why we're not getting the right characters. But again, another step forward, and hopefully you're still finding these videos interesting. Had to remove the monitor, of course, so I can get this board out to replace the faulty device. So I thought I'd just quickly show you the frame. It's fairly rigid, it doesn't move around at all, so it's not going to damage the boards or the monitor connectors, and it just makes working on this much easier. But if you're going to do this, make sure that you do something that's very rigid. It mustn't move around, and also the spacing between these is very important. If it's not correct, you'll damage the connectors on the monitor. Okay, so that's the frame. I'll get the board removed, get the device replaced, and in the next video we'll try and sort out the next fault.